Hello and welcome back to the next installment of the final exam review for Calculus 3208 presented by CDLI. And today we're going to start right into the fourth unit, which is sort of one of the most important sections of this course, all about the derivative. So we're going to talk about derivatives, and we're going to talk in this entire unit, but specifically in this session we're going to talk about average and instantaneous slope, also known as average or instantaneous rate of change. So let's get down to business. We're going to look at a couple of important things here. We're going to start with a concrete example of a rate of change, and then we're going to talk about how we can look at that as an average rate, or specifically what it means if we talk about an instantaneous rate. And we're going to talk about differentiating between the two and some ways of calculating each of those given certain little bits of information. Okay, so let's get at it. First thing we do is we have an example here. It's about an apple that falls from a tree. So the synopsis says that an apple falls from atop a 20-meter tree and is in free fall as it drops toward the ground. So 20 meters is a tall tree, but we'll take it for this example. Its height above the ground in meters is a decreasing function of time in seconds. So you can see we've got a table of values here. The height starts at 20 meters and decreases almost to 0 over the span of the first 2 seconds. And the times and heights that were given here are every half a second as the apple is falling. And here we have a little cartoon of our favorite person who sat underneath the tree and saw an apple fall and asked all kinds of questions about it, and therefore created or invented or discovered, depending on your own personal epistemologies, the ideas of calculus. So that was Isaac Newton, one of the co-founders of calculus, we'll say. So a graph of height versus time is given here, so basically all we've done is plot the points from the table, and we get a graph that looks like this. Those of you who are familiar with physics will recognize that this is in fact going to be a parabola, because what we have is the height versus time function for an object in free fall follows a quadratic pattern. So let's see what we're meant to do with this stuff now. So the first thing we're going to talk about is average rate of change. So the question we're asked is, at what average speed is the apple falling between 0.5 seconds and 1.5 seconds after it starts to drop? So what we've done here is, if you look over on the graph, this point right here represents the time and then the height that we have for the apple 0.5 seconds after it falls out of the tree. And then down here we have something similar in the situation where 1.5 seconds after the apple has fallen from the tree. And what we're asked to do is, between those two times, determine the average speed. Well, for anyone who's physics inclined, or even for those of you who aren't, you will recognize that average speed is going to be the change in height, in this case, divided by the change in time. So we can use this equation to find our average speed, and it looks a lot like the formula that we determine the slope of a line. So if you look over on the graph here, the red line that's been drawn through those 2 points is what we call a secant line. So that line is called a secant, S-E-C-A-N-T, same name as the trig function. And the secant line that we have here, any secant line basically is a line that cuts through a curve in 2 places, like the red one does to the blue curve here. And so we just use the 2 points that we have, the first point and the second point, to calculate the slope of the secant line, and that'll be another way to look at what we saw in terms of physics as our change in height over change in time. So when we do that, we determine an answer of negative 9.8 meters per second. So over that time interval, the apple was falling at an average speed of 9.5 meters per second, and of course the negative just indicates to us that it was falling downward. Alrighty. So we sometimes write the average rate of change, and this is basically what we want to get at here. The average rate of change for one variable with respect to another is, if we plot a graph of the 2 functions, one versus the other, the slope of the secant line between the 2 points that we want to find the average rate of change. And that's just basically our old friends delta y over delta x, and that tells us the slope. Okie dokie. Moving along. We can also talk about something called instantaneous rate of change. And from some of your early science courses in high school, you'll probably remember that what we're after when we talk about instantaneous rate of change is how fast is something changing at one instant in time instead of over sort of a cumulative time interval. So if we look at this example here, It's the same situation we had before, but we want to know how fast is it moving, or how fast is the apple falling exactly 1 second after it starts to drop. So if we're going to do that, we can't really draw a secant line because we're only going to have 1 point, and that's this point right here. And so what we do is we draw this green line that's given. So this green line that we have here basically is what we call a tangent line. And tangent lines are lines that sort of get close to a curve and just touch it briefly and then keep moving away from it again without actually crossing through it at that point, unless it's some special type of point. But we have some fancy ways to define tangent lines, but the most important thing for us to note about them is that tangent lines to a particular function are unique. So if we were all trying to draw a tangent line for this function at that point, and we were sort of doing it freehand, then we'd probably get a whole bunch of slightly different lines. But in truth, there's only one true tangent line that touches a curve at any one given point. Okay, so the problem that we encounter with this, and it's the same problem that Newton encountered when he was trying to determine how do I find the slope of a tangent line, well, the issue is that really we only know 1 point on that line, and that's what we call the point of tangency, right here where the tangent actually touches the curve. So you could, if you were a master of drawing tangent lines, draw that line freehand and then choose some other point out on your green line, either down there or up here, and then find the slope of the line. But that wouldn't be terribly accurate because, as we said, it's almost impossible for any human being to draw a good one of those. So what we do is we just sort of find ways to estimate the slope of the tangent line. And the way that we estimate the slope of the tangent line is just by doing what we did for average rate of change. We draw a secant. So what we're going to do in this case is we're going to choose the point of tangency that we have right here, and then we choose another point on the blue curve that's relatively close to that. So the one that we use in our examples here is we choose this point down here, 1.5, and then we choose this point up here, and we're going to draw, first of all, the secant that goes, and that's a terrible line, but you get the idea, the secant that would connect those 2 points, and we're going to say that its slope should be fairly close to the slope of the green line, so we use that as an estimate. And that's exactly what we've done over here. So we found the slope of that rough secant over there, and it turns out to be the same as the slope that we had last time. Another way to do that is to choose the actual point of tangency, as I said, and then pick another point that's close to it. So we can take the point that's actually right at 1 second, which is where these two values come from, and we can use another point that's close. So we can take this one down here, and then we'd have the secant line that joins those 2 points. And we'd get this for an answer. Now, neither one of those answers is a very good, or, well, they're not bad estimates, I suppose, but neither one of them is a perfect estimate for our instantaneous rate of change here. So what we have to do is we have to be a little bit crafty about how we're going to calculate that. Okay, so we know how to calculate the average rate of change, just find the slope of a secant. Instantaneous we know would be the slope of a tangent, but we can't do that with only 1 point, so we choose another point that's pretty close. So it says here that these 2 points that we're going to use to estimate the slope are going to have to be pretty close together so that we can get a pretty good estimate. Okay, so over the span of a month, in this example, the depth of water in a city reservoir varies with time. Okay, so the table shown gives selected values for the depth of water in feet as a function of time in days since the beginning of March. Okay, so this is the days since the beginning of March, and you can see that these are not regular intervals. They're jumping all over the place, but this is the data we have. It says in part A, what is the average rate of change in feet per day of the depth of the reservoir between the 10th and 30th of March? So this will be the 10th, and this will be the 30th. So basically, we want to find the average rate of change. So if this were a graph, I'd be calculating the slope of the secant line that goes between those 2 points. So to find the slope of that line, all I have to do is say that m equals, m for slope of course, it's going to be our change in depth in this case, divided by change in time. So that will be 27 feet minus 12 feet, divided by 30 days minus 10 days. And that gives us, in the numerator we have 15, and in the denominator we have 20. So we can simplify that. So we can say that that's going to be 3/4, or if you want, it could be 0.75, and that's going to be in feet per day. So what does that information tell us? it tells us that between the 10th and 30th of March, on average, the depth of the water in that reservoir was increasing by about 3/4 of a foot every day. Okay. In part B, it says, what is the approximate instantaneous rate of change of the depth of water in feet per day on March 23rd? So now what we want to do is we want to estimate the instantaneous rate of change. Exactly how fast was the depth of the water changing? If I were able to sort of take a snapshot of that one particular instant in time, how fast was the water changing, or is the height of the water changing at that time? So what I have to do is I have to either choose this particular point and then another point that's relatively close to it and use that as an estimate, or I could pick one point on either side of it and use that as my secant for an estimate. Typically what we do is we pick the point in question and one other. So let's take this one as our other possibility here. So in this case, we're going to say that our instantaneous slope, so I'm just going to write INST, looks like minced, but INST as just an abbreviation, and we're going to say that in this case, that's going to be about equal to, so we're going to use that fancy equal sign, and we'll have 21 feet minus 20 feet divided by 23 minus 15. So that gives us 1/8. So that's 1/8 of a foot per day is on that particular day how fast the depth of the water was changing. All right, so there's an estimate for instantaneous. Here's an example of a very similar question that you might see from a test or an exam, and it says, let DT be the national debt in the United States at time t. The table shown gives approximate values of this function by providing end-of-year estimates. So basically, it's in billions of dollars, and over here we can see that at the end of 1990, the national U.S. debt was about $3,233.3 billion. That's a lot of money. Okay, approximately how fast was the national debt rising at the end of 2005? So we know that it's rising, but how fast is it rising at the end of 2005? Well, what we want to do is estimate the instantaneous rate of change at this point. So we'll just choose one other point that's fairly close to it. So we could go just below or just above. Either way, it'll be an estimate. Let's take the point just after in 2010, and we'll say that our instantaneous rate of change is going to be about equal to, and we want a change in debt as a function of time divided by the change in time, and so that will give us 13050.8 minus 7932.7, and then we have to divide all of that by 2010 minus 2005 for our change in time. So we're using a span of 5 years here to make an estimate for the instantaneous rate of change that we want. So if you just plug that kind of stuff into a calculator real quick, we're going to get, let's see, in our numerator, 7932.7. In our numerator, we're going to get a value of 5,118.1. In our denominator, we get a value of 5. And so determining that, we're saying that the national debt in the U.S. in 2005, we're going to estimate that it was increasing by about 1,023.62, and that would be in $billion per year. That's a little bit of a scary figure, isn't it? Okie doke. So there's a test type example. So what I'm going to look at next, this is the your turn question, and it asks you to do a couple of things with those same kind of ideas that we just finished talking about. So you want to pause it and work that out. I'll show you the solution now. So here's the solution to the your turn question with some interesting details given, worked out there for you. So you can take a look through that as well if you want to pause again. And we'll just summarize all the things that we looked at today. So first of all, the average rate of change of a function on an interval a to b can be calculated by finding the slope of the secant line joining AF of A to AF of B. And so there it is. That's just our slope formula. And the instantaneous rate of change is the slope of the tangent that touches at that point. So what we typically do to estimate that is we take we take our point AF of A and we choose a second point, we'll call it CF of C, that's very close to it, find the slope of that secant line and call that our estimate for the slope of the tangent. And that about does it. So I hope that was helpful, and I hope your studying is going well. So good luck on your exams, and hopefully we'll see you again next time.